Hi, I'm Callum McCurry, and today I'm going to be talking about joint work with Jane Gao and Pavel Pralat. And the title of this work is A Fully Adaptive Strategy for Hamiltonian Cycles in the Semi-Random Graph Process. Okay, so what's the semi-random graph process? Well, you can imagine a single player which starts on the empty graph on the vertex set N. In each round, a vertex, which we'll call a square, is drawn independently and uniformly at random amongst the n possible vertices. At this point, it's presented to the player, and the player gets to adaptively select a vertex Vt, which we'll refer to as a circle, and then they add the corresponding edge to the current graph. If we fix an arbitrary monotonic graph property, for example, say the existence of a perfect matching, then the objective of the player is to satisfy this property with high probability in as few rounds as possible. So how does this work? Okay, so you can imagine squares being revealed one by one, where in each step, the player then chooses another edge. And finally, we arrive at, okay, 4 edges have been added. And as you can see, the player can now add a perfect matching on the vertex. Okay, so what's this the formal process? Well, the semi-random graph process was introduced a couple of years ago, and it can be viewed as a generalization of the Erdos-Renyi random graph process with multi-edges. So in this case, the player just chooses the circle in each round uniformly at random. All the results we'll talk about are asymptotic in nature, so we'll always assume that n is tending to infinity. And formally, we say that a sequence of events holds with high probability if the probability that it n holds tends to 1, as n tends to infinity. In this talk, we're going to focus on properties for which the player can force the semi-random graph to satisfy P with high probability in a linear number of rounds. So what does this mean? It means that there exists a strategy such that if g of t is the random graph on n formed after executing the strategy for t rounds, then gc times n will satisfy P with high probability, where c is some particular constant. So in a SOTA 2020 paper, it was shown that if you give me an arbitrary bounded degree spanning graph, then there's a strategy which constructs a copy of H in a linear number of rounds with high probability. Thus, so if we fix a specific graph, so for instance, a perfect matching or a Hamiltonian cycle, then the goal is to figure out what's the optimal linear time strategy. Okay, so in other words, the smallest possible constant such that we can construct a copy of H of n with high probability using some strategy. So in this talk, we're going to focus on Hamiltonian cycles, and we'll denote this property Ham and the optimal constant by tau of Ham. Okay, so what's previously known? Well, one thing that's quite easy to see is that the semi-random graph process can emulate the well-known K-out process, where each vertex independently connects to K distinct randomly selected vertices. So what do we want to emulate this process? Well, we want the K-out process to be a subgraph of g of t for some value of t that's, well, at least as large as k times n. And usually we want these things to be quite close to one another. So the observation is that if the K-out process has a monotonic property, then g of t has to have it as well. So it's well known that well, not well known, but it was shown a couple years ago that you can couple the K-out process with a particular strategy in this semi-random graph process, such that H of k is contained in the graph made by the semi-random graph strategy. So here, the only reason that this omega is necessary is because in the semi-random graph process, you can, of course, create multi-edges, whereas in the K-out process, the randomly selected vertices are distinct. Okay, so it's known that with high probability, the K-out process is a Hamiltonian cycle. provided k is at least 3. So this immediately applies that the tau parameter we're interested in is at most 3. In a previous work with the same authors, as well as Kaminsky, we showed that we can upper bound tau by roughly 2.61. And in this work, we provide a substantial improvement on our previous upper bound. But kind of more interesting is that the algorithm we use here is fully adaptive. So every decision made by the algorithm depends on the current history of squares and circles observed. This is contrasts our previous work where there was only really 4 or 5 kind of phases. In other words, we were really just sort of making an improvement on what was already known by Bowman and Fries. Okay, so what's known regarding lower bounds? Well, a kind of obvious necessary condition is that the graph has to have minimum degree at least 2 to have a Hamiltonian cycle. On the other hand, it was shown that there's a strategy which creates a graph with minimum degree 2 in roughly 1.21 rounds. This is due to paper in 2020. And so that immediately implies that 1.219 is a lower bound on our tau of Ham parameter. In our previous paper, we showed that this wasn't tight and just kind of improved it by a very kind of negligible constant amount. And in this work, we show that there's no reason to believe the lower bound is really anywhere close to the 1.21. And so we improve it by another 0.04. But the main kind of thing that's nice about this lower bound is that the proof is conceptually a lot easier than what we previously had argued in this other paper here. So more or less the high-level approach to our lower bound is that we show that any well-behaved strategy can't avoid creating certain structures, and then we argue that these certain structures prevent the Hamiltonian cycle from being created. Okay, so in this talk, I'm going to mainly focus on going over the techniques used to prove our upper bound, because I think they're more interesting. In all our strategies, we begin by building a Hamiltonian path. And then with little o of n extra steps, we complete the Hamiltonian path into a Hamiltonian cycle. Okay, so we're first going to analyze an algorithm called fully randomized. And afterwards, we follow up with a cleanup algorithm that includes the final little o of n vertices into the path. By combining both these procedures, we get a self-contained weaker upper bound of 2.077, so about 2.08. And we'll conclude by just explaining what our full kind of algorithm is, and the main change is that we begin by executing an algorithm we'll call degree greedy, which simply makes more intelligent decisions than fully randomized. Its downside, however, is that its analysis is quite a bit more complicated. And then so our final strategy for getting the claimed upper bound of theorem 1 is that we first execute this degree greedy algorithm for about 100 phases. Then we execute the fully randomized algorithm, and then we again finish by executing a cleanup algorithm. Okay, so all the algorithms we use in this paper, boil down to the same kind of preliminary idea. Okay, so let's suppose that we've constructed some path P of t after t steps. And let's denote U of t as the current unsaturated vertices of n. So unsaturated just means that they're not included in the current path. Okay, so if a square lands on the unsaturated vertices, then it's very easy to extend the size of the path by 1. We can just connect it to an endpoint of the path, and then in a single round, we've increased its length by 1. Okay, so let's call such a move a greedy path extension. So the interesting part about the semi-random graph process is, okay, what do we do when we can't form a greedy path extension? Well, what we'll show in just a second is that it's still possible to make a choice that's going to help us extend the path in future rounds. Okay, so let's imagine that the square lands on X. So the randomly drawn square lands on X. At this point, we're going to connect the square to some arbitrary unsaturated vertex R. And then let's suppose that at some later round, so say S, where S is greater than t plus 1, another square lands right next to X on the path. So it lands on Y. Okay. At this point, we'll connect the edge to R as well. And now what we see is that we can actually add R to the current path by adding the edges X to R and Y to R and removing the edge XY. Okay, so let's call this operation a path augmentation. What we can see is that we're now able to extend the length of the path by 1, despite a vertex never having actually landed on the unsaturated vertices. Okay, so based on this path augmentation preliminary, we can now describe our fully randomized algorithm. Okay, so here's a high-level description of how it executes. We're going to color certain edges of our semi-random red because it's going to help us just define which vertices we want to use for path augmentations. So we'll say that a vertex within the path is 1 red, provided it's adjacent to precisely 1 red edge, and it's 2 red if it's adjacent to precisely 2 red edges. Okay, so just a bit of notation. We'll denote these vertices by LT superscript 1 and LT superscript 2. And L of T just denotes all the red vertices on the path. And finally, for just sort of a technical point regarding the analysis, we need to maintain a set of permissible vertices, which are going to specify which uncolored vertices on the path we will allow to be turned red. Okay, so what does fully randomized do when it's presented a square at time t plus 1? Okay, so if it lands within the unsaturated vertices, then we just perform a greedy path extension and connect the circle to an endpoint of the path. If it lands next to a red vertex, then we're going to augment the path via an arbitrary red edge of X. And if it lands within the permissible set, then we'll choose the circle uniformly at random amongst the unsaturated vertices and color the edge red. Okay, so this case 3, it creates a 1 red vertex. And similarly, if the square lands within a 1 red, like on top of a 1 red vertex, then we'll also color, we'll draw the circle uniformly at random amongst the unsaturated vertices, and we'll color the edge red. Okay, so this converts a 1 red vertex into a 2 red vertex. And finally, if the square lands anywhere else within on the vertices, then we'll just choose the circle arbitrarily, and we can imagine this as just passing on the round because the edge isn't going to be used. Okay, so given a time step that's just defines some random variables for convenience. Here L of t is just the sum of L1 of t and L2 of t, but it's just an auxiliary random variable. The way our analysis goes is that we apply the differential equation method of McMormold to drive tight bounds on X, L1, and L2. Okay, so this method is commonly applied to analyze random processes that evolve step by step. The key point is that the step changes must be small in relation to the entirety of the discrete structure. So in our setting, what this means is that in each round we add a single edge, and this is very small relative to the current graph on n vertices. Okay, so we first need to control the one-step changes, and we call this the boundedness hypothesis. So if we let delta denote the one-step changes in our random variables, then X can't change by more than 1 in a single round. This is because we only ever add at most 1 vertex to the path. And similarly, a slightly more technical condition is that we can show that with high probability, the change to the 1 red and 2 red vertices is no more than big O of log n, assuming that the number of unsaturated vertices is sublinear, is how you can interpret it, this last term. Okay, so we now have stated the boundedness hypothesis. We now need to describe the expected differences, which control the trajectories of our random variables. So for this, we need to be a little bit careful about the history that we're going to define. And so for us, we're just going to condition on the random variables from time 0 to t, instead of the actual full history of the random graph process. And the reason we do this is because we want to ensure that the circle replacements amongst the unsaturated vertices remain independent and uniform at random. If we conditioned on the full history, then this wouldn't be the case, and it makes driving the one-step changes to our random variables much more challenging. Okay. Finally, we also need to maintain the following invariants, and we'll do this by artificially destroying red vertices. So firstly, the number of permissible vertices, so places where we can add a red vertex, is going to be xt minus 5 times L of t. And we'll also have the property that any permissible vertex is at least path distance 3 from all of the red vertices. And this is also just for convenience in our analysis, and isn't really so important for this talk. Okay, so based on this history we've defined, as well as the assumptions we made on the permissible vertices, we can derive the following kind of trend hypothesis. Okay, so firstly, if you look at the one-step changes to the length of the path, then we get the following expressions. So how do we interpret this? Well, okay, so if a square rather, lands on an unsaturated vertex, then we perform a greedy augmentation, and so this expression here corresponds to increasing the length of the path by 1. The second expression here, so 2 times LT over n, corresponds to the expected change when the square lands next to a red vertex. That's why there's a 2 times L of t here. And the final expression is just an error term that isn't so important. Okay, so this expected difference is quite nice. It's quite simple. Unfortunately, the other ones are quite a bit more challenging. So for L1 of t, you see there's many more terms, and the same is true of L2 of t. I won't go into where all these expressions come from, but the idea is that depending on where the square lands, when you perform greedy path extensions and when you perform augmentations, you end up destroying certain red vertices as kind of a side effect of the action you're taking. And so this means that there's some kind of unforeseen changes that can occur to the random variables, and we have to account for all of these. Okay, so that's, we've expressed all the expected differences. We can now write out the corresponding differential equation. So let's imagine normalizing each of our random variables by n, and we can think of s as being just some real value within 0 to infinity. If we do this, then we get the following differential equations. So as you can see here, they don't depend on n. This is it all kind of matches up to what we had on the previous slide. And finally, we have the following initial conditions. So initially, there's no vertices in the path, and there's no red vertices. So everything's 0. Okay, so if we combine these three things, so the boundedness hypothesis, the trend hypothesis, as well as the initial conditions, then the DE method implies that the number of vertices on the path is predicted by the value of the differential equation at the time point t over n. Okay, and this is true all the way up until some sufficiently large constant sigma, but this isn't so important for us right now. There's not an analytic solution to the differential equation. However, by solving the differential equation numerically, we can show that it hits value 1 when S is roughly 2.077. And so what this implies is that after 2.77 times n steps, the number of vertices in the path is going to be roughly n minus some sublinear. This is going to hold with high probability. The remaining little o of n unsaturated vertices are added to the path by a cleanup algorithm. This algorithm is based on path augmentations, is analyzed kind of a lossy elementary analysis, but the main ideas are the same. So it still is based on path augmentation, but we don't apply the differential equation method. We just use elementary concentration inequalities to argue that the remaining unsaturated vertices can be added to the path. Our final degree greedy algorithm, which I mentioned at the start, executes fairly similarly, except the red edges are chosen deterministically, and they're done in such a way to minimize the number of red vertices, which are destroyed as a side effect of path augmentations and greedy extensions. The analysis is phase-based, so there's like 100 different phases, and you can set this parameter of how many phases occur, but each phase has its own random variables, and there's many more of them, and many more differential equations. Okay, so just to briefly talk about some future work, of course, we made an improvement on the bounds, but there's still quite a large gap between the upper and lower bounds on tau. And it still seems that there's, finding an optimal strategy, it still seems quite out of reach at this point. So Alan Fries and Gregory Sorkin, they recently actually modified our fully randomized algorithm by deferring greedy path extensions. And what they do is they instead build isolated edges within the unsaturated vertices. And just this nice sort of simple change already actually improves the upper bound from what we have to roughly 1.85. So clearly there's a lot of room for improvements, and we're currently working with them to integrate their techniques with our degree greedy algorithm to improve this bound further. Okay, that's the talk, so thank you for listening.